Okay, so Bohr's model is simple. We have energy levels. We have electrons in these energy levels. All right? So we've got electrons here. We've got electrons here. 4. We got electrons here. They go in increasing outwards. Okay, now it's possible for electrons to go from one energy level to another. So we can have an electron jump up, and that is going to release a bunch of light. Right? Or excuse me, it's going to absorb a bunch of light. Wow, nobody caught that. It has to absorb light to jump up. So there's my light. Okay? If it drops back down, it's going to release light. Okay? So this is the Bohr model. Unfortunately, as soon as we came up with the Bohr model, as great as this model is, most of it is wrong. Okay? In the same way that a stick figure is wrong about a picture of a person. Alright? So if I were to draw a stick figure here, there's a stick figure. What is wrong with that picture? It's not accurate. What's wrong with it? Nobody has a perfectly round face. Nobody's that skinny. Are your legs really shaped that way? No. They're more straight and they have a bend in them. Like, there's no feet, there's no hands, there's no elbows. This is not really a very good drawing of a person. But it is a simple version of a person, and we can use it to describe some things, right? Same thing with the Bohr model. It is a simple version of an atom, and it's very, 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 very useful for a lot of things, but there are some things that are wrong with it. Okay? First off, the biggest thing that's wrong with it are the electrons. I drew little circles for my electrons here, right? Electrons are particles. They are little particles. But they're also waves. Just like light is both a particle and a wave, electrons are actually also both a particle and a wave.
Well, why would that matter?
So, why does that matter? Well, they don't really move around like they have in this picture. First off, they're constantly moving. We've never ever had an electron stop. We've never gotten them to stop. They're always moving. They never stop moving. And they move not in circles. They actually move in more of a wave pattern. Okay? So I'm going to do a quick demonstration here. So they're moving as waves. So if we take a look at this here, this would be the first energy level. So we've got electrons moving around. It's circular. Okay? Then we get to the second energy level, and the electrons have to have two waves. So they're moving around with kind of two lumps here. Now, this has more than one electron in it. So we've got one electron, two electrons, three electrons. We've got a couple of electrons going around there. All right? Then we get to the third. Notice that the third has three. Right? So it is not possible for an electron to exist anywhere except one wave, two wave, or three wave, because the electrons themselves are actually wave-like. You can't have 1.5 waves. It doesn't work. That would literally be me with the jump rope in the in-between, so I'm trying to get it going, get it at the right speed. It's just kind of wibbly-wobbly. Okay? Here's kind of a picture of that. Like, there's a perfect wave. I think that's 4. But if it's wibbly-wobbly, it's not making a wave. It can't exist there. Okay, so it will either lose or gain energy if it's wibbly-wobbly until it hits the perfect being a wave. And then it'll stay there. So that's what I mean by the energy levels. That's why they stay in those energy levels. Okay? They're waves. Now the electron is always moving. It is a wave. Here's it as a particle, but it is a wave. And they are always moving. So where are electrons? Yes. If electrons never stop moving, it's hard to draw them as stationary dots like I did before, right? So yes, we can draw them as dots even though they're waves, but they're really always moving. So where is it? You can't really say where it is. It's there-ish, right? Because it keeps moving. Every time where you're like, it's there, it's not there anymore. It's there, it's not there anymore. Okay? We can predict where it might go, and we can kind of explain where it might have been, but literally we can't say this is where it is because it's no longer there as soon as we say it. This is called the Heisenberg uncertainty principle. It is impossible to actually know the location of an electron at a given time because it's always moving. They're not stationary. So we can't really say where it is. It's there. It's somewhere over there. It's kind of the idea. Exact location, though, not so much. Right? By the way, this is called the quantum model of the atom, what we're kind of getting to here. This is our current understanding of the atom. This is as far as we've gotten. So we expand on this model still, but this is kind of where we're at today. So, moving electron again. This one's going a little faster. By the way, electrons move almost near the speed of light. Almost, not quite. But they move really, really, really fast. Now, can you see the electron?
Yeah.
Kind of. But it kind of looks like a blur, right? Like how many guys are seeing multiple at once? Yeah? So electrons are moving so fast that it's really hard to describe them as just moving around like it was in the first picture. Really, if we could see them, we would just see a blur. Just kind of flying around like crazy. All right? But where the electron is moving, it's easier to kind of pinpoint, like, it's moving in this general area, right? It's making like a sphere in that general area. So instead of drawing dots, what we're going to draw is electrons as clouds or blurs forming shapes. You can kind of think of electrons as like a fan blade. They're moving so fast, you can't really see the individual blade, but you could see like a blur. And it forms like a circle as it goes around, right? So this is kind of how we're going to describe it. We're going to describe electrons as moving quickly, so fast that it's just a big blur. Okay, we call this a three-dimensional electron cloud. And it is in fact moving in a wave form. Right? But that's one electron. It just looks like lots of them because they're moving so fast, it's a big blur. So we describe it as an electron cloud. This is basically like where the location's going to be. These can be various shapes, by the way. And, of course, various energies. We're going to have some that are energy level 1, some that are energy level 2, some that are energy level 3, 4, 5, 6, 7. Where the electron is in this cloud at any given moment, well, it keeps moving around, so we can't really pinpoint it. It's just in the cloud somewhere. Going crazy. Okay? So, there are 4 basic shapes that the electrons are going to form. The first one, the simplest one, is an S shape. Okay, the S shape is a sphere. All right, so if you guys go to the next page, there's a box there. I want you guys to draw this shape in that box, and I want you to label it. This is an S shape, or an S orbital. So that's one electron moving around. It's kind of a cloud and forming this shape. It's a big blur. Try to draw it as a sphere and not just a circle. Try. If you want, you can put sphere, not circle. Bohr is a circle. These are really spheres. It's like a big blur that's round. That's one of the reasons I put the X, Y, Z coordinate plane up there. The next shape's a little bit more complicated. It's called a P shape, or a P orbital. There are 3 versions of it. There's a version that goes left to right. There's a version that goes up to down. And then there's a version that would like come out of the screen and that in 3 dimensions. Now these kind of look like dumbbells or figure 8s, but they're like 3-dimensional. I like to think of them as peanuts. Personally, I think the P orbital looks kind of like a peanut.
Is that why it's called that?
No, but that's how I remember. P looks like a peanut. That's how I keep it straight. Okay? I will ask you guys to draw the S's and the P's. There's 3 versions of the P. Left to right, up to down, back and forth. Okay? The other shapes I'm not going to make you draw because they're even more complicated.
Oh, we can handle it.
So if you want to draw these next ones, you can kind of draw one of them in like the margarine. But I didn't give you guys space for it. So the next one is called a D shape. There are 5 versions of this one. It kind of looks like a 4-leaf clover.
Like that.
So we've got a 4-leaf clover this way, a 4-leaf clover that's flat. We've got a 4-leaf clover going the other way flat. We've got a 4-leaf clover going this way. So there's a flat one up and there's a towards you up. And then we've got the donut one. All right? So what happens here? Yes. So with this donut shape, all of these are actually like separate electrons, and I've drawn them kind of separated so you can see the shapes they're doing. But in reality, we would have all of these going around on the same atom simultaneously. So we would have this right here happening, and then we would have this happening in front of it. Trying to draw behind there. Okay? And then we would have this kind of happening here. And then there'd be ones behind it. You see what I'm saying? So these would be different electrons. The donut would also be there, and it kind of like fits all in between. It's kind of crazy.
So is there 4?
So there are 5 of these.
Okay, so is there
Okay.
like 5 number of orbitals or 5 different
5 different shapes
Okay.
of the same shape. Okay? Now the 5th shape is even crazier. This is called an F orbital. And there are 7 versions of this. Yes, Mark.
So, like, for each of the shapes, they're all, like, already in one atom?
Yeah.
Okay.
Like you would have P's, and then you'd have D's, and then you'd have S's, and they'd all be around. Like these are different electrons doing different shapes, but there's multiple electrons in an atom. Okay? So drawing all of them at once is really hard and tricky, as I just described. See that? So, now, 7 of the F shapes, these ones are the craziest. Right? Electrons will try to do the simplest shape first. Right? So they will always try to be whatever the simplest one they can be is. The only reason they can't be, say, an S shape is if other electrons are already doing the S shape. And then they have to move some of the more complicated ones. Right? So they always try to do the simple ones first, and then they move to the more complicated shapes like D and F. Here is what I'm talking about. This is a computer-generated image of what I was trying to draw a minute ago, of multiple shapes at the same time. And this is actually multiple energy levels as well. So if you look carefully here, the blue in the center, that is an S shape. The nucleus is tiny in the center, but the S shape, this blue here, that's the first energy level, and the electrons there are doing an S shape. Then we get to the second energy level, and at first we have some electrons that do an S shape. That's what this is. But then we also have in the second energy level them doing some P shapes. So up and down, back and forth, in and out. Okay, so that's the second energy level. All of these are different electrons in the second energy level. The third energy level, we only have a couple of electrons, and they're doing the S shape. Okay, so there's no P's in the third. There's no D's in the third. We haven't gotten there yet. All right? Everybody with me so far? All of these are different electrons flying around the nucleus. So here's a summary of all the different shapes. S, P, D, and F. There's one version of the S. There's 3 versions of the P, 5 versions of the D, and 7 versions of the F. Do you guys see the pattern there? 1, 3, 5, 7. It is a pattern. You probably are going to. 1, 3, 5, and 7. Now, in an energy level, in a single energy level, you can have 2 electrons, and only 2 electrons, doing the same shape, and the same version of that shape. So, we can only have 2 electrons that do an S shape in an energy level. Now that's within an energy level. So in this picture here, I have an S shape in the first, an S shape in the second, and then an S shape in the third. Right? So there's 2 electrons, and then there's 2 in the second, and then there's 2 in the third. So it's within an energy level. Only 2 electrons doing an S shape. There are 3 versions of the P. Now we can have 2 electrons doing each version. So that means we can have 6 electrons total doing P shapes. Do we follow that? 2 electrons doing every single version of the shape. So we can have 2 electrons doing each version of the D. So that means 10 electrons total, because there's 5 versions. And then we can have 2 electrons doing each version of the F. So 14 total. Basically, it's how many shapes you have doubled. 2 electrons doing each version of it. Within an energy level. Okay? Now, the first energy level can only do one shape. S, the simplest one. The second energy level can actually do 2 shapes. S and P. All versions of the P. Alright? The third energy level, you can have the 3 shapes. S, P, and D. The fourth energy level is when we finally get to Fs. Right? So each energy level can only fit so many electrons total. So the first one can only do S shapes, the second one can do S's and P's, third one can do S, P, and D, and the fourth one can do S, P, D, and F. Everybody follow me so far? It's a lot of information. So let's kind of draw a Bohr version of this. Alright, this would be lithium. Okay? Lithium has 3 protons, and this version of it, it's lithium-7, so it has 4 neutrons. How many electrons would this lithium atom have? 3. Why? Because there's 3 protons. So 3 protons means 3 electrons, right? So, that's chapter 4. 3 electrons here. They're going to be in different energy levels. So I've got 2 energy levels drawn here. They're always going to try and fill into the lowest one. All right, and they're going to fill it up until it's full. So the lowest one here is the first one. So we got an electron. The first electron is going to be in the lowest energy level. What shape is that going to form? S, the simplest one. How many electrons can I do for S? 2, right? So, in this energy level, I'm going to have 1 electron doing an S shape, and then I can also fit a second electron doing an S shape. That's the only shape that you can have in the first energy level. So the third electron can't fit in the first energy level. It's got to go to the second energy level. Okay? That's also going to be doing an S shape, by the way. Because it's in a new energy level, so it's going to start a new S shape in the next one. So we have 2 electrons doing an S shape in the first, and we have 1 electron doing an S shape in the second. If we did another one, it would also do an S shape. Because you're going to have 2 doing the S. It's always going to do the simplest shape first. Okay? And only when you have that shape filled, like there's no more electrons that can do it, or you're going to get the next shape, the more complicated one. Right? It's not until you get to 5 electrons that you even get a p. All right? Because the second or energy level actually does have p shapes. Doesn't have d's though. Okay? So this is called the Aufbau principle. Electrons occupy the lowest available energy level. They're also going to do the simplest shape first. And it's not until all of the electrons are doing that shape, like there's no more of that shape available, before they move to the more complicated shapes. So the Aufbau principle, they occupy the lowest one first. Now, a funny thing happens with the way the periodic table is actually set up. Here's the periodic table. Where's lithium? Right there. Okay? Third one, lithium. What row is lithium in? The second row. How many energy levels did lithium have? 2. Literally, these rows over here on the left, and they're over on this periodic table, whatever row, you can just count rows if they don't have numbers. That tells you how many energy levels it's going to have.
What is the top?
Okay? So you can pick any element here. Let's say bromine. Find bromine. 35? It's right there. So how many energy levels is bromine going to have? 4, because it's in the 4th row. Okay? Bromine will have 4 energy levels. 1, 2, and 3 will be completely full. Everybody follow that? 4, on the other hand, won't be completely full, but it'll be mostly full at this point. Right? Because we're almost to the end of the row, and it's when you get to the next row, like rubidium will have 5. Yes? Now, I always get that question next. Okay? What about this section right here? There's no numbers. Well, this section is actually in the wrong spot. Okay? This section on the bottom is supposed to be here. Okay? The periodic table, every periodic table you've seen is wrong. This is actually my next slide. This is what the periodic table is supposed to look like. So why have you never seen a periodic table that looks like this? Because it's too wide. And it's kind of ridiculous looking with just how wide it is. Putting it on a piece of paper, I mean, our papers are not usually that wide, and there's a lot of wasted space above and below. And we'd have to make them really small. Like this is, can you guys even read that on the screen? Barely. And it's like as big as I could get it without cutting off the elements. So this is what it should look like. And somebody a long time ago said, this is ridiculous. First off, these elements here, lanthanum through, I think it's yttrium or something like that, and astatine through nobelium. Those elements, they're really rare on Earth. Like things in this row actually barely even exist. They only exist for a few seconds. We have to make them. That's everything above 92. Those are the ones on that periodic table on the wall that are kind of whited out a little. So even the ones that are natural, they don't really exist, a lot of them on Earth. We have hardly any of them. So it's like we're never really going to use that section of the periodic table very often anyway. So somebody's like, why don't we just cut it out, put it at the bottom, and put a little asterisk next to it? Okay? Makes it a little easier to put on paper. Yeah? So periodic table, we modified it to look like this. This section here should really be right there. Okay? And there's usually an asterisk or a star. That one's got like a hashtag on it on the wall. To try, this goes here. So really, these 2 rows are 6 and 7. Okay? They should have a 6 and 7 next to them. Okay? Why don't we put 6 and 7 next to them? I don't know. They're row 6 and row 7, and there's got an asterisk saying they should be up in here. The ones that you guys I passed out to you, I think they have a little. Let me grab one. I tried to make it super obvious when I made these. You guys see the little arrow, look, these go there. Okay? Right? Yeah.
Like 13, 15, 17, 118 on like the third.
Okay, so on this periodic table, this was printed in 2013. Those elements were named in 2015.
Oh, okay.
So they were not named yet. They had they were discovered in around 2012, and then they took a while for people to like verify it, and then they were named. So on this one, they didn't have a name yet, but now they do, which is why that one on the ceiling, and the one I printed off for you guys, they have those on there. So really, I should just put a Post-it note on there, cover those up, but I haven't done it yet because I've always been too busy. So, all right, I've got one more slide for you guys to take notes on, and then I'm going to do an example problem for you, which is going to blow your mind. Okay? Principal quantum number. This is the technical term for the thing I've been calling energy level this entire time. Okay? So when I say energy level, the technical term for that is principal quantum number. It's the relative size and energy of which level we're talking about, like which energy level we're talking about. So the bigger the energy level, the further away from the nucleus it is. Okay? Now these are not circular, as I was showing a minute ago. So it's hard to say that they are far away from the nucleus because like that P shape is kind of dumbbelled. They go towards the nucleus, right? Like they move in and then out, and then in and then out, and then in and then out. So it's about like they spend more time away from the nucleus when they're in the bigger energy levels. Okay, even if they kind of move towards them a little. Right? So that's the principal quantum number. Questions? All right, time for an example problem. On your sheets, you guys see at the bottom there it says electron configurations. Okay? Oh, that's the wrong button. I am going to draw two models of an atom. Okay? So, the first one is going to be a Bohr model. The second one is going to be a quantum model. So, let me just kind of divide the page here. This is Bohr. This is quantum. Now I'm going to do the exact same element for both. Okay? I'm going to do argon. Okay? So, how many electrons does argon have? How many electrons? Nobody looks at the periodic table. How many? 18. It's number 18. So 18 electrons. Okay? So in both these pictures, I'm going to draw 18 electrons. All right? We'll start with the Bohr model. How many energy levels should I have with argon? What row is it in?
3.
It's in the third row, so 3. So let's draw 3 energy levels. 1, 2, 3. Okay? Now I'm not going to draw these for the quantum. We're going to do something a little different for that one. Now I'm going to draw electrons. Okay? The first energy level can only do one shape, an S shape. And I can have 2 electrons doing it. All right? So in the Bohr model, I'm going to draw 2 electrons in the first energy level. And in the quantum, I'm going to draw an S shape. So here are 2 electrons doing an S shape. All right? I'm color coding these to try and match them. You don't have to do that on your notes, but so I'm going to change colors. We're going to move to the second energy level now, because that's the only shape you can do in the first one. The second energy level can do S's and P's. All right? So we'll do blue. So there's 2 electrons, and these 2 electrons, what shape are they going to do? S. Because it's the first shape they're going to do. So I'm going to draw an S, kind of spherical here. All right? So there's my S shape in the next energy level. Now I've got P shapes as well. I can have 3 versions of it. So let me change colors. Let's do orange for these P's. So I'm going to draw 2 that are doing a P shape this way. Okay? And I'm going to draw these two here, that are doing a P shape this way. Okay, I'm going to draw two. This is supposed to be like out of the screen at you. So I'm going to kind of go like that, and then kind of draw it behind there. Everybody see that? So try to get three dimensionals here. It's kind of coming out of the screen at you and behind it. So 3 P shapes, 2 electrons each. That's 6 electrons total. Okay? I've drawn 6 electrons over on my Bohr model as well that are in orange to represent them. Okay? So 2 versions of the same atom. That's as many that can fit in the second energy level. So now we move to the third energy level. How many electrons have we drawn so far? 10. So we have 8 more, right? We only have 8 more. So we go to the next energy level. Why don't I do this one in green? What's the first shape I'm going to get? S. Okay, so 2 electrons doing an S shape. So here's my third energy level. S shape. Okay. And then we get some P shapes. What color have I not used yet? I haven't used purple. Right? So we're going to do 2 electrons doing a P shape going up and down. And then 2 electrons doing a P shape left to right. And then 2 electrons doing a P shape coming out of the paper and kind of behind it. How many electrons is that? 18, which means we're done. Everybody follow that? So, 2 versions of the model. The one on the right, the quantum, is more accurate, but it's really hard to draw. Now, before you guys put it away, I got one more thing to say. If I made you draw a quantum model on a test, first off, most of you guys would just draw scribbles, and it would be really hard for me to grade, wouldn't it? So I'm actually not going to make you draw the quantum model on a test. But, hold on, don't put it away. I'm not done. Instead, what we're going to use is what I like to call is a code. Okay? So I'm going to erase this. So instead of drawing this picture, we're going to use a code to represent this picture. All right? So here's the code. In the first energy level, doing an S shape, I had 2 electrons. First energy level, doing an S shape, I had 2 electrons. Then we went to the second energy level, and I had 2 electrons doing an S shape there. Also in the second, though, I had 6 total electrons doing a P shape. All right? Then we went to the third energy level, and we started off with an S shape, and I had 2 electrons there. Still in the third, we had a P shape, but this time I had 6 electrons doing it there. And that's as many electrons as I had, right? Could I have gone further and done Ds in the third, though? Yeah, if it had more electrons. So we'll get to like some Ds tomorrow. I want to give some more examples tomorrow, but this is the code, all right? It's like a little code describing what the picture is.